Okay, Craig, thank you so much for having me. So, hello and good evening. It's great to be here to talk about recent developments in the Community Snow Observations Project. I really appreciate the opportunity to contribute to this excellent workshop. And a lot of times, people sort of give thanks at the end. I want to put this right up front and thank all of the colleagues who have worked on this project with me. We have an outstanding science team, and I want to especially call out my PhD advisee, Nina Aragon, who is responsible for a lot of the modeling that you'll see towards the end of this talk. In addition to this, we have a great team of project ambassadors who are mountain guides, professional athletes, snow scientists, educators, and just backcountry enthusiasts. And they all do an amazing job of supporting and advertising this project, improving this project, and educating the public about this project, snow science in general, and also their water resources. They're all really great people if you ever get the chance to take a few laps with any of them. Okay, so basically there are three main topics I'd like to cover tonight. I will briefly introduce what the Community Snow Observation Project is all about and what role it plays in informing us about snow distribution. Second, I'd like to show some results that demonstrate that we are able to significantly improve models of snow distribution when we include or assimilate these measurements that we get from CSO participants. And then finally, I'm really excited to share with all of you that we are now running these models essentially in an operational way, and we are serving up near real-time grids of snow depth, changes in snow depth, and other snow information online. So many of you are undoubtedly tuned into this workshop because of your interest in snow as a recreational resource, and that is fantastic. But snow also serves many other functions as well. By storing snow in winter months and then gradually releasing it in the spring and the summer, snow functions as a natural reservoir. And this reduces peak flows in streams. It helps to sustain stream flows in late spring and summer. Snow also provides habitat for many species in the winter, and it helps to keep river temperatures cool throughout late spring and early summer. Despite the importance of seasonal snow, the distribution of mountain snowpacks is not as well known as we might like, especially in higher elevation, complex terrain areas. And this is due to the challenges, primarily, of making measurements in these locations. And improving understanding of snow distribution in these areas is one of the reasons that CSO was founded. Okay, so there are three primary ways in which we get information about snow distribution. Right? We can directly measure the snow using in-situ methods. We can remotely sense properties of the snow. And in other cases, we can use models to estimate properties of the snow in areas where we lack direct measurements. We are typically interested in things like snow depth, snow water equivalent, or SWE, or the vertical structure of the snowpack. So remote measurements are super cool. All right, and these can be made from fixed platforms like instrument towers, or they can be made from mobile platforms like a plane, a satellite, or increasingly these days, drones. So the general idea of this is really simple. It's nothing more than subtraction. You know, the distance between the platform and the bare ground is known. It's a known quantity. It's either measured directly or it's found by using very high accuracy GPS information. Next, the distance between that platform and the snow surface is measured in some way. And this is done by timing how long it takes a signal, usually ultrasonic sound waves or laser light, to travel from the platform to the snow surface and then back where it's received. So simple subtraction then gives you the depth of the snowpack itself. So for a fixed platform like an instrument tower, repeated measurements over time can build up a time series of the snow depth over a day, over the season, whatever time frame you're interested in. For moving platforms or mobile platforms, consecutive measurements over time can be mosaicked together and essentially build up a high-density spatial map of snow cover. So in-situ measurements are really easy by contrast. You just need a meter stick if you're interested in measuring the depth, or an avalanche probe. All right, it's that simple. You sample a few spots, make sure you're not hitting a log or a rock or something like that, and call it good. If you're interested in water equivalent, that's a little bit more complicated. You can use a coring device like a federal sampler to extract and then weigh a column of snow. So really the only limitation to in-situ measurements of snow is basically your time and effort, how long you're willing to spend out in the field doing it. So in the western United States, we're really, really well off. We have an incredible access to in-situ depth and SWE measurements. So the Natural Resources Conservation Service, or the NRCS, maintains a very large network of snow telemetry or SNOTEL sites that we're all familiar with. And these continuously monitor snow depth and water equivalent with automated stations. SNOTEL stations have varying periods of record, but a lot of them came on in sort of the late 70s or the early 80s. We have about 40, 50 years of data. Now, in addition to this, there's an even larger snow course network, which is maintained by the NRCS. And a snow course is really just a location where snow depth and water equivalent are measured manually at the same time, typically with a federal sampler, and typically this is done maybe once a month, depending upon the snow course site. These snow courses have a much longer period of record. Some of them go back 100 years. Now, in addition to these data sources, many states have their own snow survey programs, like California, for example. Many state departments of transportation are very active in collecting and publishing snow data. And then, of course, regional avalanche centers typically collect and distribute snow data as well. Now, snow models help basically fill the gaps in space and time between measurements. There's a lot to like about this approach. Computers are fast, they're happy to work overtime, they don't get cold toes out in the field, so that's fantastic. This is an image of SWE on January 1st of 2019 as estimated by the Snow Data Assimilation System, or what's called SNODAS. And so SNODAS products are fantastic. They are available for the entire continental United States at a 1 kilometer spatial scale and on a daily time step. So there's a lot of information out there, which is terrific, but there are still gaps. Snow distribution in high elevation regions of complex terrain continues to be a challenge. SNOTEL is fantastic, SNOTEL sites are great, but they tend to be in moderate elevation locations of relatively gentle terrain. And SNODAS estimates are helpful, but they're fairly coarse spatially. And also, they've been shown to perform fairly poorly in some mountainous regions. So the Community Snow Observations, or the CSO project, was started 4 years ago with the goal of filling these gaps and developing a global network of community scientists who would collect and submit measurements of snow depth. Anyone can participate in CSO, and we have a lot of participants, but we really prioritize participation by backcountry enthusiasts and also backcountry snow professionals, because these users are the ones who are out in those areas of high elevation complex terrain, which are of highest priority to us, and where we have the least amount of data. So participation in this program is super simple. You just need 3 things. All right, the first thing is you need your avalanche probe, which nobody should not have with them if they're going out in the backcountry in the first place. The second thing that you need is your phone. And really, who tours these days anymore without their phone in their pocket? And the third thing that you need is the Mountain Hub app. All right, and this is available for both iOS and Android. Mountain Hub was a startup that was founded in 2015, and the CSO project now actually owns the app, so we're sort of making changes to sort of make it suit our needs a bit better. I also do want to mention that we collect a lot of data from SnowPilot. About half of the data that comes into our program is from SnowPilot. And as most people know, this is a desktop application which is used by snow professionals. So in any event, probe, phone, software, take those 3 things, go out in the field and find some snow, and you're good to go. So that's the collection of the data. What do we do with it? Well, at the core of this is a process-based snowpack model. All right? It's actually called Snow Model by Glenn Liston and Kelly Elder. Now, this model is driven by weather data, terrain information, and land cover information. We calibrate this model using high-quality snow data, typically snow telemetry data, and we could then just run this model in an open-loop fashion, calibrated to our best case. But where CSO comes in is that we assimilate in participant observations as we get them. So when we get a measurement at some point in the snow season, if it disagrees with the model prediction, we use that error essentially as a correction to try and steer the model back towards ground truth. And this is something that is going on continuously as we model throughout the snow season. So a simple example of this is shown on the left. The dark blue line shows a calibrated run with no assimilation, and this is showing SWE throughout the year. The presence of a single observation, which is the red dot, this will drag the simulation towards that ground truth and change the time series of SWE. So at right is an example of the model output animated throughout a single year just east of town here. Early season dustings are seen, and then we see the strong growth of the snowpack throughout midwinter, and then the eventual melt out in late spring and early summer. So in most regional to national scale snow modeling efforts, observations from automated snow station networks such as SNOWTEL are the primary source of data that are simulated into snow models. Now, from a mountain snow perspective, one problem here with these networks is that they are typically located in accessible locations that are not at risk of hazards such as avalanches. And because of this, many alpine and remote mountain areas are missed. And so this is where the value of CSO observations really becomes apparent. CSO observations provide a source of in-situ data in complex terrain that we would not get otherwise. So in this figure, looking at the canyons east of town, you can see we have 4 SNOWTEL sites that lie within this modeling domain, but then you sort of see this sea of blue points. And these are all CSO observations that have come in over the past year in this domain. So does any of this actually matter? Does it work? I mean, this is the idea, but let's actually see if it works or not. Will these observations actually improve our ability to model high mountain snowpack? So we tested this in the following way. We did 4 sets of runs, which only differed by the choice of what data, if any data, we assimilated into the snowpack model, ranging from no data to everything that we could find. So these plots compare modeled SWE to observed SWE at 2 typical SNOWTEL sites. The y-axis is showing you the SWE depth, the x-axis is showing you the day of the water year. So the red line is the observations, that's the SNOWTEL data. The dark blue line is the open loop run if we assimilate in no data. And then the light blue line is what happens when we assimilate in both CSO and SNOWTEL data. And you can see that that ends up giving us a better result than if we assimilate in no data. So there are 2 main findings here. First, the assimilation of CSO data on its own improves modeled SWE compared to the best calibrated snow model run. And then secondly, the assimilation of CSO data in addition to the SNOWTEL data improves the model results beyond what we would get if we had just SNOWTEL data on its own. Okay, so this is impressive in the sense that SNOWTEL data is daily. We get a measurement every single day. CSO data is really random in space and time. It's opportunistic. People are just out on a tour and take a few data points and send it in. And we aren't controlling that. So this organic data does a really good job at improving our models. So this animation here shows you the difference between the modeled snowpack with assimilation and without assimilation. If it's green, this is basically telling you that the assimilation is making the snowpack deeper, and if it's brown, this is telling you that the assimilation is making the snowpack less deep. And so these changes that we get constantly throughout the year are important in terms of making the models be as close to reality as possible. Okay, so these experiments informed our data assimilation scheme. That's great. This is what we just launched this summer, which is mountainsnow.org. And what we're doing here is we are basically serving up in near real time high-resolution model data. And we're doing this because this is what our participants asked for from day one. So this is the Mountain Snow app, all right? This is the homepage for Mountain Snow, and you can see that we've got these presently 9 different modeling domains scattered across the country. We do have one out in New Hampshire. I know it's a bit lonely out there, but we're really grateful to the people out east who take the time to contribute to this project. So let's go ahead and zoom in on Utah and sort of see what's going on. Okay, so first, as with all things Google, you can choose between map, satellite, or terrain as your base layer. That's done at sort of up at the upper right. And then with that Layers tab up at the upper right, you can also adjust the transparency of whatever layer that you're looking at. So here, for example, we're looking at SWE, and I've made it sort of semi-transparent so you can see the terrain underneath really nicely. Another thing that you can do is you can use the date slider to go look at whatever day that you want. All right, and we started archiving these data on October 1st of 2020, and we basically have them up till not today, but basically 2 years before today is the most recent time slice that you can go and look at. You can toggle on or off other sources of snow information as well at mountainsnow.org. And so here what I'm showing you is I'm trying to drive home the point of the value of this high resolution information. So on the left are our simulations. Okay, I think it's 50 meters. And on the right, I'm showing you the exact same day what SNODAS says is going on with your mountains. And this is at that 1 kilometer resolution. And so you can see that the mountain ranges basically get just lost with SNODAS and things get kind of smeared out. So it's that really high resolution that we're really shooting for. Other things that you can do is that you can use these controls on the left to essentially control the color bar. So you can sort of like slide the max value down or up, and you can sort of make the picture kind of look sort of the most intuitive to you in terms of giving you the best look at what's going on with your snowpack. You can also enable at Mountain Snow various satellite views of the snowpack, such as sentinel imagery or MODIS reflectance data, which is sort of a proxy for snow cover, and it has a resolution of about 500 meters. So the way that we built this is that these satellite views are computed as 7-day averages. And we do this to allow for satellite revisit times that might be longer than 1 day, and then also cloudy periods. So you can get the 7-day average satellite product maybe showing slightly different snow boundaries than our model product because it's showing you a week-long average, whereas we're showing you what's going on that particular day. So 2 other things I want to mention. You can turn on essentially a 72-hour snowfall layer. So this is something that's going to show you the change in the snowpack over the past 3 days. In this case, this particular example I'm showing you is showing you the change in snow between just last month, the 9th and the 12th of October. All right, and you can sort of see with the blue that we have a lot of positive change in snow. If it was red, it would be a negative change in snow. So you can kind of use this to look at areas where you might have heavy loading. And then finally, the last thing I want to show you is that we can actually show you the difference that community participation makes. So this grid here is showing you the difference between the modeled snow with a simulation and the modeled snow without. So where it's blue, the active people contributing snow data is nudging our snowpack depth up to a higher value, and where it's red, again, the active people participating is making the snowpack a little more shallow. And you can see that we have changes in this both in space, and then with that animation I showed you earlier, changes in time as well. So to kind of wrap up, I just want to mention that none of this is possible without the community. If people don't show up and participate in this project, then it's just me doing a lot of programming on my own. So it's really, really important that we sort of build and sustain networks of people that are willing to sort of put in a little bit of effort with the idea that creating better models of snow distribution benefits everybody: recreationists, forecasters, water resource planners, and so on and so forth. So with that, I'd just love to say thanks very much for your attention and be happy to answer some questions. Back to you, Craig.
Awesome. Thanks for that, David. And I know we've been trying to get together here for the past couple of years. So glad we connected the dots. I got to tell you something, between your talk and Travis and Trent's talk, I don't even think I'm smart enough to ask a question. So the beauty of this forum is that we do have people who can type those in and text those in. So keep those questions coming. And the first one is going to be to gain accurate spatial data collection, how many in-field depth measurements need to be taken?
The answer to that is really surprising. It actually ends up being not that many. So, I showed you a couple of different simulations. I showed you some results for an area, a domain here in Utah. And if I go back and look at the data records for the past year, maybe we had a few hundred submissions that came in from the project. And if we assimilate all of those 200 or 300 in, it makes the model amazing. If we assimilate in just 20 or 30, it makes the model still pretty amazing. So it actually doesn't take that much participation.
Excellent question. Very accurate answer. And so, is this model solely used for backcountry riders, or do you see any cross-pollination with agricultural forecasts, climate studies, anything along those lines?
Yeah, the answer to that kind of depends on how big of an area that we model and sort of how finely resolved do we make that model. So if we start to model larger domains, like the Teton domain is pretty big, our Central Oregon domain is pretty big, we start to attract some interest from water resource planners who kind of want to know how much water is stored in their watershed. If we model a smaller domain, like the one we've got going for Utah here, we can model down to a spatial resolution of like 25 or 50 meters. And all of a sudden, that resolution becomes much more valuable to like a recreationist who might just want to like look at one particular canyon and see how deep the snowpack is there.
Fantastic. So maybe a couple of different applications there. This is going to be a two-part question. So the first, familiar with smart probes, what are your views on that? And then secondly, will there be any, or do you have any automated probes that can help you with this research, maybe make your job a little bit easier?
So, Craig, was the first part of that my thinking on smart probes? Was that it?
Yeah, exactly.
Okay.
Exactly.
Yeah, so Mountain Hub actually kind of came out of a company that was dabbling in that years ago. And smart probes, I think, are great in concept, and they're getting better year after year. I have one. It's not as long as some of the other ones, so its utility can be a little bit less in sort of Pacific Northwest snowpacks where we get 4 or 5 meters of snow. But I think that they do have a lot of value, and they're showing a lot of promise.
Fantastic. And again, keep those questions coming in. Does the mass balance of the in-situ or model total water equivalent equal stream flow measurements during spring runoff?
Well, so to close the mass balance, there's more than just the snow, the rain and snow coming in, the stream flow going out. You have things like sublimation and evapotranspiration and so forth. We've done this kind of modeling in other areas over larger domains where we have kind of worked out all the aspects of the mass balance, and we've even gone so far as to kind of compare our sort of annual estimates of snow storage to GRACE satellite data, which is another really cool tool for understanding just how much snow and ice you have in a particular domain.
Got it. Okay. And then kind of like the garbage in, garbage out question here. What are you doing to help filter human input that could maybe be inaccurate for some reason? So are there any filters that are in place?
Yeah, that is probably the question that we get asked the most often. And what I didn't, I do have a slide on it, but I don't want to show it at this time. It was at the end of my talk. What we actually do is we take all of the measurements that come in from SnowPilot, from Mountain Hub and other sources, and then we compare, so those are all stamped with the time, they're all stamped with the location. So we actually go and we compare the reported snow depth on that day and at that location to other sources of information like SNODAS, for example. And SNODAS isn't perfect, but by looking at the correlation between the measurements that we get and estimates from SNODAS and other sources, we use that as a tool to try and screen out what are obviously outlier points.
Okay, excellent question. Thanks for that answer. And then David, how does the community snow corrected data compare to just the remote satellite-based measurements only?
It gets a little difficult to compare our output to remotely sensed satellite data. Well, I should back up. It depends on what we're comparing it to. We can compare our snow cover to things that we see in Sentinel, and it's quite good. Or we can compare our snow cover to what MODIS says is snow-covered area, and it's also quite good. There are other satellite products out there, like the ICE-SAT-2 satellite, which actually, it's like LiDAR on a satellite. So it's actually measuring the elevation of the snow surface. It gets difficult to make comparisons between ICE-SAT-2 and what we're doing in terms of that satellite has only certain tracks on certain days, and it gets very hard to make a substantial comparison just because there aren't that many opportunities.
Got it. And then, hey Dave, what's the future of this research? And then kind of dovetailing off of that, how long will this research need to take place to get a really super succinct, accurate data set?
So I think that where we're going with this is we started off as a small pilot project up in Alaska near Valdez, and we have sort of built this out now with all of these automated tools that allow us to sort of quickly set up, calibrate, and then start doing assimilative runs at any domain in the United States that we want. And so we would like to sort of continue to build this out to, right now we're doing 10 domains, we'd like to see by the end of the year maybe doing 15, maybe doing 20. And we do this in areas where we sort of see the demand. So we kind of rely on the backcountry community to sort of be out there and start submitting data. And when we start to see a lot of data coming in, that tells us, number one, there's a lot of people traveling in that area that might like this type of snow information. And number two, there's a number of people that are willing to take a little bit of their time and sort of help us out. And so we kind of like to give back in those areas.
Fantastic. Just as a quick wrap up, Dave, if you could, since this is such a community-based observation system, if you could just give a shout out to how folks could either get in touch with you or become part of this program.
Yeah, so the number one thing to do is to just go to communitysnowobs.org. And if you go there, we have tabs on that website that sort of, number one, give you tutorials about how to do it. But then number two, sort of give you places to go to get additional information on the app, best practices, all those kinds of things. And we have the usual social media where people can find us and they can sort of keep up with updates about what we're doing.